This video is going to show you how to perform a chi-squared goodness of fit test. Consider this example. CBS, ABC, and NBC are the three main news networks. Between the three, we think CBS gets 40% of the market, ABC gets 25%, and NBC gets 35%. We randomly sample 1,000 people and ask what their preferred network is. We want to know, are the hypothesized proportions correct at the 5% level of significance? The problem that we run into here, though, is that we're working with categorical data. We're working with proportions. But this is a single population that has more than two categories. Neither of the tests that we've covered so far that work with categorical data can handle more than two categories. As a result, we need another type of test, which is going to be the chi-squared goodness of fit test. The chi-squared goodness of fit test involves a categorical variable with at least three categories. We assume that each category gets a certain percentage of the sample space. These become our hypothesized proportions that end up in the null hypothesis. From there, we collect data and we sort the responses into their respective categories. These are the actual counts that we'll use in the test statistic. What we'll do is we'll compare the observed responses to the hypothesized proportions to determine if our hypothesized proportions are actually correct. The goodness of fit test has a framework for the null and alternative hypotheses. They're not actually going to be set up exactly as what you see on the screen here. We have to adjust it based on the variable that we're working with. But in a nutshell, the null hypothesis reflects the fact that all of the hypothesized proportions are correct, while the alternative hypothesis reflects the idea that at least one of the hypothesized proportions is not correct. And again, don't use this exact wording. It's only meant to give you an idea of how the hypotheses are set up. Each problem's hypotheses are going to be unique to the context of the problem. So for this particular example, where we're looking to see if the hypothesized proportions, 40% for CBS, 25% for ABC, and 35% for NBC, are correct, we'll set up the hypotheses as follows. The null hypothesis is going to be that the proportion for CBS is equal to 0.4, the proportion for ABC is equal to 0.25, and the proportion for NBC is equal to 0.35. The alternative hypothesis is that at least one network has a different proportion of the market. We won't necessarily know which one is different. We won't necessarily know how many of them are different. The alternative hypothesis is just like the alternative from the ANOVA. At least one network has a different proportion of the market. Now to continue this problem, let's take a look at the data. After surveying 1,000 people, we find that 440 people primarily watch CBS, 230 of them watch ABC, and 330 of them watch NBC. Again, we're looking to identify if the hypothesized proportions are correct. So our strategy here is to compare the observed counts from the survey, the 440, 230, and 330 above, to the expected counts if the null hypothesis is true. How many people would we expect to watch CBS, ABC, and NBC if our hypothesized proportions are actually correct? If the null hypothesis is true, then the actual counts that we got from the above data should be close to the expected counts. They're probably not going to be perfect, they're probably not going to be equal, but they should be in the ballpark. Here's the notation that we're going to use to calculate the test statistic. We'll have a total sample size of n. The number of categories in the variable that we're looking at is equal to k. And the hypothesized proportions are going to be denoted p sub I for each category. We'll calculate the expected counts, e sub I, by taking the total sample size and multiplying by the hypothesized proportion for each category. Then the test statistic follows a chi-squared distribution with k minus 1 degrees of freedom, and it's calculated by taking the observed count for each category, subtracting off the expected count for each category, squaring the difference, and dividing by the expected count. We repeat this for each category in the variable and sum each of the individual terms to come up with our final chi-squared test statistic. Here are a couple of notes about the test statistic for the goodness of fit test. Large values of x squared are evidence against the null hypothesis. The reason for this is that it implies that the observed and the expected counts are far away from each other. Notice that in the numerator of the test statistic, we take the observed minus the expected counts and square that difference. If the observed count is already far away from the expected count, then squaring that difference is contributing a very large amount to the value of x squared. On the other hand, small values of x squared support the null hypothesis. Small values of your chi-squared test statistic imply that your observed counts and expected counts are relatively close together. As a result, the goodness of fit test is always going to be an upper one-sided test. At this point, we're almost ready to calculate the test statistic. The only thing missing is the expected counts. The expected counts are calculated by taking the overall sample size, 1,000 in this case, and multiplying by the corresponding hypothesized proportion for each category. So the expected count for CBS is going to be 1,000 times 0.4, which gives us 400. We would expect, if the null hypothesis is true, that 400 of the 1,000 people would primarily watch CBS. We repeat this for ABC. The expected count for ABC is 1,000 times 0.25, which gives us 250. And for NBC, the expected count, 1,000 times 0.35, which gives us 350. Now that we have the expected counts as well as the actual counts, we can calculate the test statistic. The test statistic, again, follows a chi-squared distribution, and is calculated by taking the observed count minus the expected count squared, divided by the expected count, and summing these results for each individual category. Our first term involving CBS is going to be 440 minus 400, difference squared, divided by 400. We repeat this for ABC. ABC gives us 230 minus 250 squared in the numerator, divided by 250. And for NBC, we have 330 minus 350, that difference squared, divided by 350. Each of these individual terms, when worked out, gives us 4 plus 1.6 plus 1.14 for a final test statistic of 6.74. The last thing that we need here are the degrees of freedom. The degrees of freedom are calculated by taking the number of categories in the variable and subtracting 1. In this case, our variable has 3 different categories, CBS, ABC, and NBC. Subtracting off 1 gives us 2. So this is a chi-squared test with 2 degrees of freedom. And finally, we can calculate the p-value, make our decision, and come to a conclusion. Using Excel, we'll find that the p-value of this test is 0.0344. Since we're doing this test at the 5% level of significance, we'll reject the null hypothesis because the p-value of 0.0344 is less than 0.05. And the conclusion that we come to is that at least one network gets a different proportion of the market than we originally thought. Notice that this conclusion is very similar to the conclusion that we came to in the ANOVA. In ANOVA, we could only tell if at least 2 means were different, but we couldn't tell specifically which means were different. In the chi-squared goodness of fit test, we can tell at least one of the proportions is wrong, but we can't specifically tell which proportion is incorrect if we reject the null hypothesis.